Hi, my name is Bill Fortney, and thank you for being here for the final tool on telling is dataset A different from dataset B, a t-test on means. And I love this tool because it's going to tell us definitively, is there a difference? And what's the probability of the difference that we see happening if they're really the same? So we get a lot of information. We don't always need it, but when we do need it, it's important to have it. Okay, so we've seen the first tool, we just compare individuals visually. The second tool, we put a confidence interval on the average and we compare those visually. And now the third tool is going to be the t-test on means. Okay, before we jump into this, I told you I would talk about T. You saw that earlier. Now, you remember when we learned about the normal, we found the z-table, which gave us the probability of getting a value. So like a probability of z from here being a z of 2 with the probability was 2.28. Okay, now this is when you know population parameters. We're dealing with samples. We're always estimating population parameters. So what statisticians developed is they came up with this t distribution, which you use when you have sample data, which is what we always have. So everything we're doing is always with the t. And you're like, well, why have we been using z in the 2? You'll see why in just a second. Okay, so the t-test that we're doing is using this distribution right here. Now, we're not going to have to look up values. Excel is going to do that for us. But this is where it's getting them. It's not coming over here and getting them from the z. Although it is the exact same thing. It's the probability of that occurring based upon the number of standard deviations you are away. Okay, so you remember on the z, we said 95% was approximately plus or minus 2. Well, in reality, 95%, that's 2.5 on each side, is 1.96. But we've been using 2 anyway because we're an engineer, not a scientist. We're not getting the exact. We use 2 because it's convenient. Now, over here on the t, here's 2 right here. And there's a bunch of values. Well, over here, the probability is based upon the number of standard deviations you are away. In the t, it's based upon the number of standard deviations you are away and the number of samples that you have. It's called degrees of freedom. There's an equation that gives you your degrees of freedom based upon your experimental design. And so notice, if I have about 5 samples, the t-value would be 2.5 instead of 2, or if you want to be specific, 1.96. We've been using 2. What do I mean? That's your multiplier. That's k. So over here in the t world, if I had 5 samples, I would multiply it by 2.5 if I was doing a 95% interval. If I had 10 samples, I'd multiply by 2.28. If I had 20 samples, I'd multiply by 2.086. Again, you're not going to be doing that multiplying. The t-test, that's going to be done for you. But I just want you to see that's where it's coming from. And I said this earlier, that's the difference between the engineer and the scientist. I'm perfectly fine when I'm trying to decide this to multiply by 2 and know that I'm in the ballpark enough to tell what I need when I'm putting like confidence intervals on individual things. The t-test we're doing is going to do this exactly in Excel. Okay, so now let's say we have 2 averages, not heat treated. Whoops, go back, and heat treated. Here's the average. We've put confidence intervals on those because we know they're normally distributed. That tells us what to expect within each one. Now we're wanting to know, is this between difference consistent with what we would see if there's just randomness, or is that between difference between the averages a special cause? So here's what we're going to do. Let's assume there's no difference. Heat treating and not heat treating, they're the same. Heat treating did not matter. So I have a hypothesis. It's going to be called the null hypothesis. Average 1 equals average 2. If we're talking population, mu1 equals mu2, okay? They're exactly the same. Now, assuming that's true, what would you expect if I took this average and subtracted it from this average. Think about that for a second. I'm hoping you would say, well, I would expect to get a value close to 0. Because if they're both the same, then yeah, I may get an average here or here, but you remember that the error bars are pretty small on the averages. So I'm going to get a value close to 0. Yes. So this is the distribution of the difference. So this is the distribution of average 1 minus average 2, or average 2 minus, whichever way you want to say it. But this is the distribution of the averages. So here's my no heat treated, here's my heat treated, there's the standard deviations. And so that the difference between those two is also going to be random variables, because the initial things I subtracted were random variables. So I'm going to take these two standard deviations and average them and say, you know what? This difference is going to have about that standard deviation. The average is going to be 0, because if there's no difference between the two, I would expect it to be 0. There's a standard deviation. So I can put on here what I would expect to find in terms of the amount of difference. 95% of the time, I would expect the difference to be in here. It can go out here some, and then 99, I'd expect it to be in that. Well, let's see what the difference really was. If there's no difference, this is what I would expect. So let me subtract them. So here we got number 2 minus number 1. It's 946, which is way out there. And that's actually 5.5 standard deviations away. So was my hypothesis true or false? The evidence says my hypothesis was false. If my hypothesis was true and there was no difference between them, when I subtracted them, I would have expected my actual difference to have fallen within here. It didn't. It fell like way outside of there. That's the essence of the t-test right there. We're going to assume they're the same. If they are the same, then we know what to expect based upon the standard deviation. We're going to calculate what it really is. We're going to look at how many standard deviations we are away and see how it fits within here. Now, one thing I want to point out. Yeah, let me throw this in right here. You're going to see this thing called P. I'm going to show it to you again. What that P is it's the probability of me being this far out and further. It gives me an idea of what was the chance of getting that number if they really are the same. If they really are the same, what's the probability of me being this far out or further? That's going to be P. Okay, now what I was going to say is I need to make one disclaimer here. This is not how you calculate the standard deviation. There's a statistical way that combines them based upon all the theory of statistics. So the true combined standard deviation is 246 instead of 174. It's a little bit higher because it's factoring in all the chance things, all that stuff happening. In our case, even then, this is way out there, okay? I just didn't want you to freak out thinking, wait a minute, when I looked at it in Excel, I didn't get the same thing as when I averaged the two. That's because that's not how Excel is doing it. Okay, so let me formalize this. So an alpha level t-test, what's alpha? That's our probability. Do we want a 95%? Do we want a 99%? And so that alpha is telling us, okay, what percent is over here? What percent is over here? So if it's a 95%, I'm saying, okay, 95 in here, 2.5 and 2.5 here, okay? Now, let me show you where that alpha comes in. The null hypothesis is they are equal. The alternative hypothesis is they're not equal. So here's what I'm going to do. My t-statistic is going to be how many standard deviations away am I really? Here's my distribution of the combined. It should have an average of 0 and a standard deviation no more than here, all the way out to here. So if it was 95, roughly 2. I'm going to calculate my t-statistic the difference between them divided by the true S combined. So that's going to be the number of standard deviations I am away. If my t statistic is past where I said, so the red is my cutoff. If I'm the red or beyond, I said I wanted an alpha level, that's alpha over 2. If my t statistic is in here or further, this did not happen by chance. There was a special cause. My null hypothesis is false. The averages are different. If I reject the null hypothesis, if I'm in here, if my t-value is inside of my alpha level, so this would, in this case, within this 95% range, then I have no evidence to reject the null hypothesis. I can't say they're equal. In statistics, accepting a hypothesis test is weak. I can't say they're equal. I just can say I have no evidence to reject and say they're different, okay? So when you're seeing results, this happens in medicine a lot, and they tell you that they didn't reject. That's not saying they're the same. It's saying they didn't have evidence to say that they're different. Okay, remember I told you about the p-value. The p-value would be the probability of getting this number of standard deviations away or further. And that's going to be a real help to us. You'll see that when I go through some examples. And then I just throw up on here to show you there are other kinds of t-tests. We are doing the basic t-test on 2 averages. Okay, so we have our 3 tools: compare individuals, compare averages, and the t-test. Now, let me show you how to do this in Excel. And if you don't have the data analysis, you'll need to go into options and add the data analysis pack. Everybody gets it. You can Google and see how to do that. So you're going to go data analysis. If you don't have it, go to options, add-ins, Excel analysis tool pack. You're going to come down here and see 2 tests, two sample assuming unequal variance. I always assume the variance of standard deviations are equal. It's going to open up. You highlight the data for heat treated. Then you highlight the data for not heat treated, whatever 2 things you want to check. You put in the hypothesized difference. We're always looking at 0. You put in your alpha, whether you want 0.5 or whether you wanted it higher, and you give it an output range. And remember, there's alpha over 2, alpha over 2. That alpha, half on each side. And then when you say go, bammo, here's what you're going to get. Now, I'm showing this to you up here. This is what we had before for our average and standard deviation because I want to relate it. So if you notice, here's my average, there's my average, here's my other average, here's my variance. What's that? Variance, remember early on, variance is standard deviation squared. This reports variance instead of standard deviation. If you squared those, you would see these match. How many observations I have, hypothesized mean difference, and you see my degrees of freedom number that I told you? That's what it's using in that t calculation. Now, there we go right here. So here's my t-stat. The number of standard deviations, the mean of set 2 is from the mean of set 1. It's our t-stat. The difference between them divided by the S combined. And it's 3.9. So that's like saying, okay, here it's out here 3.9. Right here is my critical value. That is my value at the alpha level. So if the t statistic is bigger, like either that way or on the left if it's negative, then you're 95% sure the null hypothesis is false. They're not equal. So this is my critical value, 2.1. My t-stat was actually 3.9, so heat treating mattered. These 2 data sets are not the same. And then there's my p-value. So what this is saying is the probability of getting this value or beyond, if they were really equal, is 0.1%. There's a 0.1% chance that heat treating didn't matter. That's really low. I'm not going to get this big of difference if heat treating didn't matter. Okay, so you see the t-test, how powerful it is in terms of the information it gives us. So I'm going to just show you a couple examples. This one, here is my t-stat. It's 7. Well, of course it's 7 because look, this is a no-brainer. We can see just with individuals it doesn't matter. We can see with our confidence interval, our average, there's a big gap. So there's a 3.9 e to the minus 7 chance that we got this much difference and they're really equal. Okay, let me bring them up a little bit. You see now these are overlapping. Now my averages tell the truth. Tool number 2, I would be like, yeah, they're definitely different. Let's see our t-test. Our t-stat is 3.9 and our t-critical is 2.1. Our p, there is a 0.1% chance that we would get, yeah, that did not happen randomly. You see, we didn't need the t-test because this told us, okay? Now we're going to overlap a little bit more. Now the confidence intervals on my average don't really tell me. So I go to my t-test. My critical is 2.1. My t-stat is 3. So that did not happen randomly. There is a, let's say, there is a 0.6% chance that I would get that much difference if the averages really were the same. No, the averages are different. Heat treating mattered. Okay, let me go one more. Now you look here, there's a pretty big overlap. There's a pretty decent overlap right here. What's our t-test showing? Our t-critical is 2.1. Our t-stat is 2.28. So there is a 3.5% chance that I got this given that they're equal. Now, if you're doing a 95% confidence interval, a 95% confidence, you're pretty sure that heat treating made a difference. So from the pure t-test, our t-stat is bigger than our t-critical. We would say heat treating mattered. Okay, let's go one more. Now our t-stat is 2.1. Our critical is 2.1. Our t-stat is 2.17. Notice there's a 4.5% chance. Now, for me, as an engineer, the t-stat says, yes, it did make a difference. If there was a lot of money riding on this, I would probably do a little bit more experimentation before I made a huge decision with it being that close. In theory, I could say that heat treating mattered. I get a little bit nervous when they're real close like that, just me personally, if it was a huge, huge, huge decision. And then we'll do one more where now you notice our t-critical is 2, our t-stat is 1.4. It's actually behind. And look, there's a 15% chance that that happened just purely random, that there's no difference at all. Okay, so you see, that's the t-stat. And it gives us that p-value, which is so helpful in knowing. Now, you remember the glue problem. I did the t-test on the glue problem. So look, SG and PW. There's a lot of overlap, but we come down here, our critical is 2.4, our t-stat is 2.6. There's only a 3.8% chance they're different. Yeah, I would be pretty good okay saying PW was different. VC and PW, same thing, about a 4% chance. And then look at SG and PW. There's a 57% chance. We already knew that, remember? I mean, we saw that in this graph, we saw that in that graph. But that's how the t-test can give you that definitive information to know. Okay, so that's it. You have the 3 tools that you need to say, is the data same or different? And I just encourage you, keep it in the context of this full analysis. Don't forget when you go to draw your conclusions to look what conditions hold true. And hopefully you're seeing the design of your experiment is critical, because if you don't hold variables constant, if you don't measure them, then you may see things in your data but not have the information to analyze that. Or you may want to be able to draw conclusions for certain conditions, but you didn't include them as variables. The design of your experiment is critical, so be careful with it. Brainstorm. Don't jump to your first idea. Oh, we could measure this. Remember the principle of design. Your first idea is usually not your best. What is it you're trying to accomplish? What do I need to measure? Let me brainstorm ways to do it. Let me analyze those. And as you do, you will learn to design experiments, to analyze the data well, to get information that can allow you to sleep well at night with the decisions that you make. I'll do one more video for you, and it's going to be going through an entire example and then using all these tools for you.